Okay, we can get going. More people will come in as we go, I'm sure. So welcome everyone. This is the 5th workshop from the LandAware Working Group 8. And we have we have 3 different, let's call them mini seminars today, presented by 4 people. So the last seminar is going to be 2 speakers. And Luca is not here today. For those of you that have been coming to this, he's on paternity leave for the next couple of months. So I'm getting to take care of everything. He will be back in June. So if you've been following along, the workshops for Working Group 8 have been covering different topics. I thought I'd just give a quick overview about LandAware for those of you that are less familiar. Up until last year, 2022, it had 8 working groups actually. The original 7, and then the one that Luca added on IoT-based methods and modeling. And as of 2023, working groups 2 and 6 are no longer active. They were there for 2 years, they accomplished their tasks, and they moved on. So we now are left with these 6 working groups this year, and then maybe some will disappear next year and new ones will come again. But if you are not familiar with it, LandAware is just a network-based group that's focused on landslides and all of these different topics. So if you're interested, please look at landaware.org to check it out. You can sign up. Specifically, Working Group 8 is focused on IoT-based monitoring. And our objectives through these workshops and other events is to promote the application of innovative and traditional sensors in the Internet of Things framework for landslide early warnings. We've been having lots of seminars where people are sharing their experiences, and we're going to see more of that today. From all 3 of our speakers. And then we've been having discussions and talking a lot about starting pilot projects. So this is something Luca and I are still working on, and we'll continue to communicate as we make progress there. The activities are webinars, workshops, seminars, and then networking. And so I'll just go to the next slide. But in terms of networking, if you want to join Working Group 8, I guess rules is not necessarily the best topic for this heading, but how to do it maybe is you need to register at landaware.com, and then you can sign up at Working Group 8. And we would ask, if this is the first time that you've joined one of our workshops, if you could take out your phone right now or take a screenshot of this slide so that you can then scan this QR code later and fill out a questionnaire. This is how we find speakers. We use the information in here to sort of give us an idea of where we should go next. So please fill that out. The timeline is as follows. We are now in April 2023. I think many of you are probably familiar with the EGU, which is also coming up this month. Luca will be there, and there are some LandAware activities, so pay attention to your email and the LandAware LinkedIn page. There'll be updates about that. And then we're still trying to organize or get funding so that we can hold a physical meeting here in Oslo in September. And the one other thing I would mention that Luca asked is to point everybody to the JTC1 workshop that's going to be in Oslo in 2023. So this summer in June. Have a look. There will be a lot of interesting topics and discussions going on there. So the agenda for today, we're going to have 3 talks. The first 2 talks are each approximately 20 minutes, and that includes maybe a question or 2 at the end. And then we'll have a slightly longer talk from Dr. Venkata Uday and Varun Dutt, who are joining us from IIT Mandi, India. Before that, so we have Arthur Charlety, is a PhD student at the University of Grenoble at East Terre is the lab. And then we have Dr. Pina Peternel, and I apologize if I mess people's names up, who's at this Geologic Survey of Slovenia. So after those three talks, we'll then wrap up and we'll have some time for a discussion if people have further questions or want to talk about things. So I don't have any more. Are there any questions before we jump into the first talk from Arthur? Okay. Then if not, oh, Luca is here. Cool. Luca, do you have anything you want to add?
No, yeah, it's perfect. I'm just listening. Maybe if someone is coming to EGU, there will be an event on Thursday evening, and please check LandAware website so that you can register yourself. We are booking and making a reservation to a restaurant. Yeah, that's it.
Great. Thank you. Okay, Arthur, please go ahead and share.
Okay, can you hear me?
Yes, we can.
Yes, perfect. So can I start?
Yes, please.
Yeah. So hello everyone. So I'm Arthur Charlety, PhD student in ISTER, as was said before. I work with Mathieu Le Breton, Eric Larose, Laurent Baillet, and Olivier Michel in the ISTER lab, mostly. And so today I will be speaking about a portion of what I'm doing in my PhD concerning machine learning approaches applied to improving RFID landslide monitoring. So this might not be clear to everyone what is RFID, so I will start by defining it. So RFID stands for radio frequency identification. It is a way of identifying goods. This was created in this objective. So the main application is retail and in industry supply chain monitoring. But recently it has been more and more applied to agriculture, medicine, and also importantly, earth sciences. It's been investigated for many different applications, as you can read if you read the review from Mathieu Le Breton that is cited on the bottom left. So the main advantage of this RFID technology is that it is standardized. It is produced with billions of tags every year. The cost is extremely cheap. And they're really easy to deploy because the systems of deployment and monitoring exist and are really well defined. So this is the main motivation for this application of landslide monitoring. So first, before going into detail, I would like to give you the main highlights of the presentation. So what I want to show you today is that RFID landslide monitoring is possible with the centimeter accuracy in terms of displacement monitoring in both 2D or 3D dimensions. One of the big advantages of RFID is that it provides a sub-hourly resolution, so you can estimate at a very fine time scale. And also you have a space oversampling because you can basically deploy any number of tags you want on the reading field. What I want to show you in terms of machine learning approach is that Kalman filtering is one method that can really improve the quality of the data. And also that in order to synthesize the information, spectral clustering approaches can be interesting for understanding the kinematics of landslides, be it in terms of space or in terms of time activation of the different blocks of the landslide. So now that I gave you the highlights, let's go a bit deeper into the presentation. So now, how do we measure displacements using RFID? So basically, the principle is the same as an extensometer, for example. We use what is called the phase of arrival, which is indicated here by phi, the Greek letter phi. So basically this phase corresponds to the accumulated phase over the traveling of the radio frequency wave from the reader antenna to the tag and back from the tag to the reader. So using the equation that you see on the left of the screen, we can link the evolution of the phase during time to the evolution of the radial distance between the antenna and the tag. So if you look at the middle scheme here, from position T1 to position T2, the phase phi1 and phi2 give us information on the displacements projected on the radial direction, which is the vector dr. And so this is why I said it's comparable to an extensometer, because it gives you simply a distance between a fixed point and a moving point on the ground. And so here on the right, you can see unwrapped phase series. So the phase evolves in time, and we see that over the first few months, we see a displacement which is quite rapid, and then quite slow creep of the landslide. So that's for the basics of what we do. Of course, there are other displacement monitoring methods or ranging methods, but I will not go too deep into those now. So now, where do we apply such RFID monitoring techniques? So one of the sites, over several other sites, is the Armalières landslide, which is located in the southeast of France, close to Grenoble. It's a quite big retrogressive landslide, and a small portion of it was equipped with RFID 2 or about 3 years ago. The RFID site is very close to the headscarp of the landslide, because we need fixed ground to position the antennas. And so you have a top view here of the RFID field with the 4 antennas placed on fixed ground, and the RFID tags placed on moving ground, with the headscarp indicated by the dotted line. So if we see, so here on the new picture, you see that the antennas have a quite wide aperture in terms of horizontal distance, but also in a vertical distance, because the point of this equipment was to try to monitor the tags in 2D and 3D, and not only to use them as extensometers, to use the method as extensometers. So the 4 antennas and about 30 tags that are spread over this field, with an acquisition rate of about 100 measurements per day, depending on the power supply, of course, because this station is autonomous. So we can't really measure instantaneously at every second. So okay, that's it for this slide. So now the main principle of this method is, of course, to look at the landslide displacement from the side. So here you see the antenna aperture is directed towards the perpendicular direction from the landslide main direction, in order to use the phase, the difference in phase variations from each antenna to obtain the displacement of every tag. So this is in the middle plot. This is the displacement of one tag over a little less than 1 year. So from October 2020, so it started here, to August 2021, with here screened 2 reference measurements taken by tachyometry. And so you see that the 2D displacement is quite well reproduced, with what we estimate to be little less than 1 centimeter in error. So this is for one specific tag, but now you see the displacement field of the whole of a set of tags here over this period, with RFID results and reference measurements. So you see that we can have an estimation on the spatial deformation at the meter scale approximately with this method. So yeah, that's it for it. So now how can we improve this method with Kalman filtering or other machine learning approaches? This is the question I've been trying to tackle. One of the questions I've been trying to tackle during my PhD. So one way to improve the RFID information is to filter it through the Kalman filtering approach. So I don't know how familiar you all are with Kalman filtering, but let's consider it as a black box that basically takes in measurements and also assumptions about the system that we're measuring. The assumptions can be geometrical, physical, linear or non-linear processes. Here I use non-linear, which is called extended Kalman filtering. And so basically the Kalman filter will find an optimal solution between the measurements and the model assumptions in order to, for example, when the measurements are too noisy or just simply too bad, to propagate the system using the assumptions. And so the Kalman filter will provide as an output, of course, the positions of the tags, the velocities, and also, which is very important, the quality of the measurement, the quality of the estimation of the state. And so this is one of the main interests in our opinion for the Kalman filtering approach, is that it provides a covariance estimation. So we can know at which level of confidence the state of our system is known for now. And basically the assumptions we use are simple continuity assumptions. Time continuity, the fact that the velocity will most likely propagate from one instant to another, but also spatial continuity, the fact that two very close tags will share the same behavior. So that's a broad definition of the Kalman filtering approach. And so now what does it provide? So the output is simply a displacement output. So here on the top graph, you see the output for two different tags that are positioned on the same object, the same stick. So basically the RFID tags are placed on such sticks, and we have two tags per stick facing the antennas. And so here you see that along time, the displacement of the upper tag corresponds to what we could expect from a landslide behavior point of view, but it differs from that of the lower tag. And so if we were only using deterministic approaches, we would have trouble knowing what's really happening. Is the landslide really advancing from in less than 1 month of about 20 centimeters or not? The advantage of the Kalman filter is that it provides a covariance estimate, and so on the bottom plot you see a posteriori covariance estimate of both states, so both tags. And so we see that in this situation, the lower tag presents much higher covariance estimates. Reminder that this is a log scale. And so on a very application point of view, we can know in this situation that we should discard the information from the lower tag at that time, because basically the confidence in the state is quite bad, but we can use the upper tag as a reference in this situation. So that's one great advantage of the Kalman filter. And we don't see it here precisely, but it also provides a higher stability in terms of noise managing, noise processing. One other interesting application of the Kalman filter is what is called phase unwrapping. So I don't know how familiar you are with phase wrapping issues. when using satellite interferometry, for example. But basically in RFID, we have the same issue because phase is basically wrapped around a circle of 2 pi. So generally it is cycles of 2 pi, and one very important process in recovering the displacement is unwrapping, phase unwrapping. And using deterministic approaches, unwrapping the phase can lead to issues, especially when you have intense displacement during a period of bad measurements. For example, if you have high multipath interference in your space. And so this is where sometimes the Kalman filter can be of use, because by propagating the velocity of the tags, because of course the tag will not go back 10 centimeters in one day. The landslide doesn't go go back to its previous states. So here on the figure, you see two different displacement series. One which doesn't use the Kalman filtering approach, and you see that in the beginning of February there is a step which doesn't make a lot of physical sense, and also doesn't correspond to the reference measurements. And you see that using the Kalman filter, the velocity is propagated and the phase unwrapping is correctly performed, as is shown by the correspondence between the reference and the displacement series. So yeah, that's one good advantage of the Kalman filter, one other advantage. So that's what I wanted to show you about the Kalman filtering approach. Of course, we can discuss it more afterwards. One other method that is interesting when analyzing RFID information is data clustering, because RFID is, as a lot of IoT technologies, it provides quite a lot of information, and with a high redundancy. So when you have, let's say, hundreds of tags, it is quite hard to analyze each and every tag to understand the whole setup. So one way to synthesize the information is to use what is called clustering. And so what I used here is spectral clustering, which is basically a method of creating subsets of points in a space by basing ourselves on a metric of similarity. So what tags behave similarly in the same space and at the same time? So basically that's the question I'm asking. And what I use to have a metric for this is the correlation of velocities. And so when you correlate velocities, you see that some specific blocks of tags behave together. And so you can identify geomorphic blocks that will activate together at specific space and at specific times. And so you can discriminate blocks also like spatially, but also time-wise. So this is also an interesting method when you want to identify what triggered the activation of the landslide. If let's say the top moved first or the bottom moved first, and what triggered the whole activation. So yeah, it was just an overview of this, and we can also, of course, speak about it later. So to conclude this short presentation, let's wrap it up. So I hope I managed to show you that the Kalman filtering approach can be of use in RFID monitoring, especially using the covariance estimation, which provides an information about the quality of the measurement and of the estimation, and that also spectral clustering can be of use in order to synthesize the information and to get space-time discrimination of the landslide activity. For the perspectives that we're doing towards the end of the PhD, we are investigating multi-method investigation on this Armalière landslide, using notably RFID and ambient noise seismic information. But also one big aspect is the localization of tags using drones and UAVs in order to have bigger dimensions, bigger monitored areas. So thank you for listening. I hope I was clear. And if you have any questions, I let 1 or 2 minutes for this. Thank you.
Yeah, thank you very much, Arthur. Are there any questions? Yeah, Tina.
Yes, I have one. Thank you, Arthur, for your presentation. I would like to ask you if this refit is it's appropriate for vegetated areas. So if we can measure displacements in the areas that are covered with forest, for example.
So that's one of the advantages of RFID is that when you have a vegetated cover, you can still measure the displacement and the position. Of course, the presence of vegetation can generate multipathing and let's say a loss in the quality of the estimation. But yes, and that's also one of the points of the UAV approach, is that we could deploy RFID tags under the let's say trees, not too high trees, but yeah, and still monitor them. It can also work under snow. That's also a big advantage. But as you see here on the 2 images, the vegetation really evolves during the year, and we can, without too many issues, monitor the displacements through the seasons, even with snow, even with the growth of vegetation on the fields. Of course, it depends on the type of vegetation, but yeah, the main principle is that it works under vegetation.
Okay, thank you.
Thank you. Okay, any other questions? Then I think I'll save my questions for the discussion. Thank you very much, Arthur. That was very interesting.
Thank you.
Tina, you're up.
Okay, thank you. Just a minute, please. Can you see my presentation?
Yes, we do.
Okay, great. Hello, everybody. My name is Tina, and I'm from Geological Survey of Slovenia. And today I would like to talk about one of the largest landslides in Slovenia that pose a very high risk to the settlement. Before I start with this landslide area, I would like to represent you some background information about landslides in Slovenia in general. So even though that Slovenia is a quite small country, it has very dynamic morphology and also geological and tectonic conditions. And all these factors contribute to high susceptibility to landslides. So according to previous studies, 1/3 of Slovenia territory is very high susceptible to landslide, and consequently 1/5 of Slovenia population actually lives in area that are highly prone to this kind of slope mass movements. According to our landslide database, there are more than 5,000 registered landslides in Slovenia. Recent data showed that in the last 10 years, landslides have caused damage amounting to about 350 million euros. The damage caused mainly affected infrastructure, agriculture, land, and facilities. The most common phenomena are shallow landslides, as you can see in the figures below. that are mainly caused by intense, short or long-lasting rainfall events. So even though that Slovenia is prone to shallow landslide, today I will talk about area that is actually prone to deep-seated landslides that have a potential to mobilize into the breeze flow. So we will talk about the hinterland of Koroška Bela, that it's located in northwestern Slovenia in the Karavanke mountain ridge. And this area has more than 20 landslides. 5 of them are larger than 8,000 square meters. Urbas and Chikla landslide that we can see on this panoramic view are the most active one and are the most largest landslide in this area. And also I will represent in this presentation these two landslides. So these landslides pose a direct risk or threat to the settlement of Koroška Bela that lies below these villages. That lies below these landslides, and this area is very densely populated. So there's more than 2,000 people live there. It has also very well developed industry and infrastructure. It is also very interesting that this settlement lies on the alluvial fan of past debris flow events. As you can see also on this figure, it has a typical shape of an alluvial fan. So the activity of this landslide can be also evidenced on the field. The area is characterized by the subsidence of the local road. Then we can find also numerous of tension cracks that are spreading more than half of a meter per year. We can also observe plenty of ponds and curved trees. Also, historical sources, books describes that this area is known to have experienced several debris flow events in the recent geological past. One of the most recent one happened in 18th century, and it caused the destruction of the buildings and cultivated areas in this Koroška Bela. So here is one timeline. In this respect, we are observing this area since 2006. We have been doing investigation under different projects, from research projects, European or technical, but in general, this investigation can be roughly divided in 2 stages. So before 2017 and after 2017. Why 2017? Because in April 2017, another debris flow event happened. Actually, part of the Chikla landslide collapsed and turned into debris flow. This particular event didn't reach the settlement below, but even though this event represents additional warning sign that this area is a source area of potential debris flow. So this event, like I said, happened in April 2017 due to a precipitation event. It was the closest weather station showed that in 2 days there were around 200 millimeters amount of rainfall. So the comparison between 2 digital evaluation models before and after event showed us that the estimated volume of eroded material was approximately 5,000 cubic meters. So before that event, the project were mainly focused on scientific. And after this event, a lot of projects were more technical, were implemented with the goal of developing and implementing mitigation measures. So here we can see the map of all investigation that we did in this area. As you can see, we did geotechnical, then hydrogeological, geophysical, and geodetic measurements in different time periods. We also performed several trenches located on Karoshka-Bila alluvial fan in order to obtain data on past debris flow events. So all this investigation allowed us to design detailed engineering geological maps, cross-section, and 3D models. So this is one of the main results that we designed. So engineering geological maps. Here we have a map of landslide Urbas, and the landslide Urbas covers an area of approximately 180,000 square meters, and it has a maximum sliding surface which is around 25 meters. Here we have a cross section of this landslide, and as you can see, it's quite complex. So we are talking about a composite landslide. So the upper part, or the minor scarp of this landslide, was formed in dry talus material below the steep limestone ridge. In this part, the sliding surface was estimated to be 23 meters deep. The central part consists of tectonically deformed and weathered clastic rocks with very low geomechanical properties and permeability. And in this part, the landslide is depth around 10 meters. So the most active part of this landslide is actually the lower part, where we can find a mixture of these tectonically deformed, fine-grained clastic rocks and covered with a huge amount of talus material. So additionally, stream Bela contributes significantly to the mobilization of this sliding material downstream. So I would like to point it out that also all the inclinometers along this cross section were cut in few months due to landslide activity. The next landslide was landslide Chikla, and this landslide covers an area of approximately 26,000 square meters. But it's quite deeper. Although this landslide is much smaller than the Urbas landslide, it's much more active, which is also known by past events. Moreover, the path from the landslide to the settlement is shorter and more narrow. So also here I will quickly represent you a cross section. So the sliding mass of this landslide consists mainly of debris material which were deposited as a result of some fossil events. This material consists of silty gravel with the limestone blocks. From the boreholes and inclinometers, it was evident that the maximum sliding surface is at the depth of 28 meters. So here we also can see some pictures, and you can see that there's a lot of material that is prone to the debris flow. So in order to assess the dynamic of this landslide, it was crucial to implement a flexible and reliable real-time monitoring system. So to achieve this, we place different, let's say, low-cost geotechnical sensors. And this consists of, for example, wire extensiometers And the landslides, both landslides, are also equipped with the GNSS antennas, as you can see on the left figures, which are permanently installed on this fixed on this location across the landslide bodies, and there are also some local reference units outside of the landslides. We are also having a lot of piezometers, and we are obtaining real-time data about the groundwater table. And both landslides has their own, let's say, base station. This base station provides firstly power, and also they provide in situ data storage. Here are two examples of our base station. So to address the potential risk of landslides, it was essential, like I said, to establish continuous monitoring system. And this system serves as the basis also for a local landslide warning system. With this local landslide warning system, we are trying to detect landslide activity and what could be the impact of this landslide activity. In order to achieve this, we establish a customized dashboard, as you can see on this figure, in order to provide access to all these real-time monitoring sensors. This dashboard is updated hourly and can be accessed by our team from Geological Survey, and also some other stakeholders can access to this website. In the future, we would like to improve this warning system with additional sensors and also with some threshold values and warnings. So here are also some figures from our web camera that is installed in the Chikla and Turbas landslide. So additional to the real-time monitoring data, we have also some periodic monitoring and some sensors that needs to be measured manually. So we are doing inclinometers. There are some few inclinometers left that are not destroyed. Then we have some basic crack meters and very basic snow gauge system. So the main purpose of this research is to recognize what are the main landslide triggering mechanisms. And with the monitoring data, so we used real-time monitoring data, and with this monitoring data, we made kinematic models, which were correlate with the hydrometeorological parameters, which are the groundwater level change and precipitation. And with this correlation, we did really simplified dynamic model, and I will briefly represent findings in the conclusion. But before that, I would like to point it out that even though that a lot of research and equipment have been implemented in this study area, there are still some uncertainties regarding the landslide dynamic in this area. And these uncertainties are mainly related to short monitoring period. The monitoring period is about 3 years, which is relatively short. And during this time period, there were no extreme precipitation events, like was in April 2017. So in the future, we need to maintain this monitoring. in order to provide more comprehensive and reliable data on landslide dynamic. The second problem is, or issue is, sensors outages. So we are dealing with a lot of outages due to that this area is located in a remote and mountain areas. So we have some issues with the power supply, especially during the winter. Another thing is that landslides damaged a lot of sensors. Like I said, we have also periodic monitoring data, for example, in clinometers, and these measurements are quite irregular because the area is quite remote. We cannot provide regular measurements period. The first analysis showed that the dynamic of these two landslides really vary along the landslide area, and basically they are primarily influenced by local geological and hydrogeological conditions. So certain parts of the landslides are at different stages of development and respond totally different to the same external triggering factors. For example, like intense rainfall events or long-term precipitation or groundwater table change. In addition, the moderate or high seismicity of the area could be another predisposing factor that could contribute to the occurrence of the landslides. We didn't deal with that. Anyway, the additional and continuous monitoring is essential, is needed, especially on the main body of the landslides. We have some issues which monitoring system can be implemented due to that landslide is very vegetated. Also, I would like to point it out that continuous measurements of the Bila stream flow and measurements of the snow cover would be also an important improve of our understanding of how snow and surface water affects to the landslide dynamics, particularly in the area of the landslide which are prone to the breeze flow. I hope I was clear. Thank you for your attention, and if there's some question, I would be glad to answer.
Okay, thank you very much, Tina. Are there any questions?
Yeah, I have a quick question, Tina.
Yes, please.
This is Uday. So actually, I just wanted to know what should be a typical length of the wireline extensometer which you are using.
Sorry, what?
What is the typical length of the extensometer?
The typical length of the extensometer is actually a few meters, actually. Okay. As you can see on this picture, it's this one. It's approximately 5 to 6 meters. Meanwhile, this one is around 3 meters.
Okay, thank you.
Thank you.
There was another hand, but was that Jeffrey?
Yes, good evening. I would like to know what is the sensor that you use in the UAV? Or only use RGB?
So the sensors that we are using are GNSS, wire extensometers, and piezometers that are real-time monitoring and web cameras.
Okay, but when you use the drone, only use RGB.
Yeah.
Okay.
In the case of drone, yes.
And what is the frequency when you are flying that place?
For that place, at the main scarp of the Urbas landslide was actually this part was actually the only one part appropriate for the photogrammetry.
Okay.
And it was one measurement per year.
Okay. Okay. Thank you.
Thank you.
Any other questions? Okay, then thank you again, Tina. I think we will move on to the last presentation so that we have a little bit of time for discussion at the end. So Uday or Varun, I don't know which one of you will share your screen, but please go ahead.
Yeah, I'm just showing it up.
Uday will share his screen.
Yeah, I hope it's visible.
It is.
Yeah, thank you.
And Uday, you can make it into the presentation mode. We are seeing
it's taking a
Right.
lag. Still you are seeing.
Okay. Yeah, we are still seeing, at least I'm seeing the side window with the slides in small as well.
Yeah, just a second. I will try to change it. Okay, I think now it should.
Yep, now it's fine.
Perfect. Okay, thank you. Very good evening, and probably some part of the time for all of you. So this is I'm Uday, and my colleague Varun is in the call. So we are here to discuss on the development of an indigenous landslide monitoring and early warning system, which we have made possibly for the first time by using MEMS and integration of IoT. Slightly, I will say, on the other line, that most of the sensing what we have seen can be slightly into the surface, but we are talking about something which is very near to subsurface. Very near to the surface. We are not talking any major part on the surface, subsurface related system in this particular presentation. So with this, I will just try to take you around the presentation on the point. So quickly, I'll just try to show you our campus of IIT Mandi. As you can see in this particular figure, we are in the mid Himalayan region, almost at the level of around 1,000 meters from the sea level, up to around 3,000 meters on the sea level in the mid Himalayan region. We have campuses separated by around 5 kilometers, where we have to travel a lot to reach to the second site. And in this, while we are traveling in this particular area, of course, we are going through snow peaks. We also have a beautiful river across this campus. So the major point which I want to discuss as a part of this is, when you're traveling across this road, you are seeing most of these calamities or most of these landslide activities which keep on happening on the site. Very close to these slides, you can see the roads. So we travel on this particular road on almost like day-to-day purposes. And as you can see quickly on the type of the slides which I want to highlight here is, again, the type of surface flows, a very small thickness of the slide which comes in, but the area or the extent is too large, as you can see in this particular image, including the same again. Okay, apart from this, yeah, we have some areas which are covered with rock, and then you will see some areas where the debris is coming out with a mixed debris, where we have boulders to almost near to fine-grained soils which come out of this particular location. So we are living in this particular area. We travel on these particular lines on almost a daily basis. So this becomes a major motivation for us, that we need to see how we are reducing the risk associated with these landslides happening across. And one major thing which happened somewhere in 2017 is this landslide, which is called as Kotropi landslide, which happened in 2017, which took almost like 46 lives because of two bus which were traveling on this road, which got carried away by the debris. And if you can see the debris, this has run down almost near to 1 kilometer downstream, and thank God, you know, a major settlement here were not affected because of this particular slide to happen. So now we are talking about how to control this risk associated with this landslide. So that's where we started to work on most of the efficient technologies. Apart from this, we try to understand always it's not a good idea to go into a structural measure, because a landslide which I just showed you, which is 250 meters, it's difficult to be structured or controlled with any structure, and the cost involved in this is going to be definitely more. A simple alarm about the happening of the happening of the landslide would have solved most of the issues. So that's what we have started to work on, different types of measures, and we found that there are some regional scale and local scale monitoring, of which we tried to talk about rainfall thresholds. Then we also have data driven models. We also try to work on field scale monitoring, and lastly we are also talking about a simulation or perception of the local communities on how they want to take it further, depending on the landslide areas where they are staying. So based on this, we have come up with this particular system of landslide monitoring technologies, where we talked about all the systems, right? Like a few of them already have been covered earlier to this particular presentation. So we are talking now about a slightly lower cost MEMS based, as I just told you, and we are also using IoT, artificial intelligence, machine learning as a part of integrated monitoring system for these landslides to develop the early warning system based on the monitoring what we are doing at the site. So our system typically contains of some sensing units. As you can see here, we are measuring the atmospheric conditions, including temperature, atmospheric pressure, light intensity, and rain, because we are saying that the rain is a major trigger factor of these particular landslides in our area. Apart from this, the major causative factor is a capacitive soil moisture sensor. So we also have a capacitive soil moisture sensor which is reading, and we are going again by a displacement based sensor, which is mostly by using a three-dimensional accelerometer, also gyroscope, depending on this. And this is the PCB board where the sensors are connected or mounted on our circuit. Slightly later, I'll be showing you also the sensing box which we have made out of the whole setup. And then the whole system or the integration of this particular cloud talks about having a system mounted on a particular hill where we are noticing cracks, or we are noticing most of the deformations or maybe creep formations or the main scrap formations, etc. We try to identify these locations. We go to the site, then we install our system, and our system is of course solar powered, and it has no need of any connections, but wirelessly we are connected, or we are saving all the information on the cloud. So on this cloud, we also have a thresholding system which is presenting the warning as per the requirements. And further, we are seeing how these particular warnings will reach public, as well as some hooter and blinker messages which we can give at the site itself. Yeah, so before we go to the site, of course, we need to see how the sensors are working. So we quickly went into calibration of the sensors. The soil moisture sensors are directly measured in the lab. I'm sure all of us know these methods, but how to look into this particular sensing, that is the MEMS based accelerations. I'll quickly run this video. I'm not sure if you'll be able to hear it. There is no sound associated with this. So quickly you can see that there are some signals which are generated in this particular point. So we will try to see when the slide starts to happen, then I'll be seeing that changes in the signal. So mostly I'll talk more or less the signals which are very near to what we have heard from Arthur. However, yes, when the signal starts to come, then I see the measure of the movements coming in. So I want to understand how these signals can be further nurtured to understand what type of velocities and displacements are happening, which I'll show you in the next slide. So one more slide which I'm trying to show. On the top, you can see is the displacement and the velocity profile of the slide which is moving. However, because the video has been fastened to 10x, you will not be able to probably see exactly the velocity which is probably coming in, but there is a small disturbance on the velocity, which means it's able to measure the velocities again at a different scale altogether on this. So by this, we are able to calibrate how these particular sensors are giving me the displacement as well as velocities before they are taken to the site. So at the site, we are trying to develop the alert based on the monitoring which we are doing. Then we are also trying to predict by using machine learning. And also, as I showed you, we are also alerting or warning by using different levels of alerts, or by using text messages as well as on the site. In a typical location where we have installed our location, where we installed our sensing, you can see that a set of movements slowly, which we designate as small movements, start to convert to moderate. So this changes we are trying to see, or we are trying to do with respect to the intensity of the message, intensity of the signals we are getting. from the acceleration sensors plus frequency. So we want to see how quick we are getting signals, as also how large are the signals with respect to different movements, as I just showed you in the video just before this. So going ahead, our sensing system typically looks like this. This is the box where all the components of PCB are mounted, whereas all the sensors run into the soil by using these wires. And we want to install in a place where we are sure that there is a chance of landslide happening. So we also have an alerting unit, which is in the local language here. It also beeps and gives you sound as well as some light to especially warn people at the night. In the morning time, it's fairly good enough to listen the sound from here. So this is the Kotropi landslide, which I was just showing you before at the start of the presentation. And on this, we go to the site, we install our sensors, and you can see also our students working day and night to look into the code and how to verify it as per the requirements at the site. We also have demographic or graphical representation of the data, which is coming from this system, and it is directly saved in the cloud, so that we can also take into the look at various conditions. So now when we are looking at some case studies, I quickly wanted to make sure that yes, whatever we are doing at the site is reaching to the people. So that's where all the administration who is corresponding the district management or the disaster management authorities of the district, they are looking at this particular systems and they are trying to take an action how to control people getting into the location. So you can see very clearly that we have warned a particular system and it has been covered in the local information. And also there is one more location, which is Kupa, which is again in the same Himachal Pradesh of India. So this is again one more location where we have seen some unexpected movements happening in the site. So we have warned the people, and that also has cleared a landslide which happened in this. So apart from this, we have a registered case. This happens to be the campus which I just showed you at the start of the presentation. So we have a sensor which is very near to this place. You can see, there are a few locations at which we have shallow landslides. So we also have our sensors put in this particular place, and we started to give the warning somewhere around 8 o'clock to say typically at the night, and somewhere around 9 o'clock and the same day we see that there is a warning saying that there is a landslide which happened on this particular road. So we try to avert a major disaster happening right in front of our campus itself. And one more in the same location, as I was saying, very near to this particular location. So on 6th of August, on the same year of 2022, the same location, earlier it was here, now we are talking about this particular location. We again gave a warning saying that there is a moderate movement, and which has converted to large movement immediately. So we alerted this place, and at around 8 o'clock in the morning, and then very near to 12 p.m. We saw that this particular landslide has happened. Heavy landslide occurred on this particular road. So we are having very few case studies, very much case studies in the earlier monsoon 2022. We have averted major disasters by using our landslide monitoring system. So apart from this, we go on ahead. We want to see on the regional scale as well. So we are also measuring rainfall as a part of the system. So we are able to also give rainfall alerts very, very well in time. So we wanted to map out how many landslides are happening and how they can be best suited. For example, our system is a very site-based or a very point-based measurement which we are doing. However, I want to see if it can be integrated with a satellite image. So we started to work on to INSAR-based analysis. So on INSAR, we are trying to see the deformation profiles. So for example, in this particular location, I have my system installed in this particular location. Then I want to see for some corresponding to how the satellite is showing me the deformation in the scale of displacement in mm, whereas our system also is able to detect the movements almost very near to the mm scale. So we want to see how, or we want to understand how good our system is in integration with the satellite image, so that instead of simply using a point, we can able to increase its grid length based on the satellite image, which we are able to get from INSAR. So this is what we are trying to look at the area of Kinnaur, which is again in Himachal Pradesh, including the same valley which I just showed you is Kaman Valley, that is at very near to IIT Mandi campus. So now I will hand it over to Varun to look into the machine learning aspect of the data.
Yeah, thank you, Uday. So this is Varun. If you can hear me, just checking.
Yes, Varun, you're audible.
Okay, great. So this is on prediction via machine learning. So when we put sensors and we get data, we've been collecting data for now several months and across several geographic locations. So before we go in to do machine learning, we wanted to get an idea on what are the parameters, particularly civil geotechnical parameters, which are kind of causing slides. So one of our students who's close to finishing his PhD went and sampled some 60 odd locations and along the same road. And some of them were where slides had already occurred. And so they were disturbed locations, and some locations where slides had not occurred undisturbed. And we kind of using geotechnical analyses estimated some of these parameters. So these are the max and min values. And next slide, please. So what we did was we tried to do feature engineering, which is basically identify factors which would be so among these different variables, which are those variables which correlate to some extent or are responsible for identifying a movement landslide class from a no landslide class. And then using those factors, we attempted to do machine learning. So the figure on the top left with the orange bars are kind of showing the correlation coefficients of different parameters with respect to the movement or no movement class. And as you can see, relative compaction, porosity, field water content, KS, and angle of internal friction seem to be highly correlated. And then what we did was we took combination of factors, because individually these factors play a role. So we started doing combination of, say, only one factor, then one with the other factor, then three factors, then four factors. And basically, we tried to use a machine learning approach, decision tree and random forest, to kind of see if we add one more factor to the mix, how does the accuracy of this classifier improve? So you can see that there is a thresholding effect around 5 factors when kind of the classifier saturates. So these 5 factors seem to be as a compound unit seem to be more responsible. Next slide. Yeah. And then kind of looking at that, we can come up with these data-driven maps and stuff. So you can see that in this table, relative compaction, slope, angle, porosity, in C2 water content, saturated permeability, angle of internal friction seem to be the most responsible factors. Of course, and some of them, like in situ water content, are things which are more dynamic, which led us to estimating the rain at that location and the moisture using the capacitive moisture sensor. Other factors are more or less geotechnical, which can be evaluated, and we may not change too much from one season to another. Next slide. So yeah, so these are kind of the data which we get from the different systems deployed. And as you can see, this data comes in real time every 10 to 15 minutes. And the data consists of weather variables, accelerometer values, gyroscope values, moisture content, and also soil stress. Next slide. So we've kind of looked at, so before we developed our own system and put it, because data was still coming in, we wanted to see if we could we could use machine learning on an existing system. So for that, we have actually borrowed data from another location, which happens to be on this Uttarakhand road, Chamoli Badrinath road, and then we also deployed our own system. So these are just maps showing some of these locations from where we have already taken data, or we have collected data using our sensor system. Next slide. Yeah. So before we go into, we do data pre-processing and stuff, we've tried a number of architectures, and particularly machine learning architectures. And here you can actually see some architectures like PCA autoencoders more focused on linear and nonlinear feature selection. Whereas then we have architectures like long short-term memory models, which are more recurrent neural networks which have memory in them. And why we need memory particularly is because oftentimes history of movements, like some of the case studies which Uday was showing you, movement is happening over the last 4 hours, and then it leads to a slide. So, history of movements, prior movements, oftentimes is responsible for the next movement or maybe correlated. And then also oftentimes rainfalls of different days in the past may cause a slide on a certain day. So we've come up with some novel architectures where we first do feature engineering using an autoencoder, and then we take that into an LSTM, or we build pipelines of LSTMs, particularly this bidirectional stacked LSTM. So we've tried different ideas. Next slide. Yeah, and here we have looked at particularly two things. One is, how much is the movement, which is a regression problem. And the other approach is, just classification of movements, whether these are, whether there is movement or no movement, and if there is movement, of what magnitude, large, moderate, or small. So we've tried this on different sites where we have deployed the technologies. So for example, this is an example at Dharampur along the Kalka railway line where we have the system deployed in the pictures. And you can see that there is a trajectory of approximately 1 year. The orange line is actually the actual movement. And around the 110th or 115th day, there is a large movement of about 3 centimeters. Whereas the dotted line is the movement predicted by the BS-LSTM model. So the model is very accurate in predicting movements which happen on a daily scale. Next slide. Uday? Yeah,
Yes,
now
sir.
I can see the next slide. Yeah. Okay, so there was some delay. So so here we have some results from classification exercise, which I was telling you, looking at, just movement versus no movement of soils. And you can actually see we've tried different flavors of, vanilla LSTM, a linear feature engineered model, and then followed by a non-linear feature engineered DRA LSTM, which is dimensional reduction autoencoder LSTM, and its test accuracy is better than the training accuracy. So basically, these models, particularly DRA LSTM architecture, is very accurate in terms of predicting the next movement, which is say approximately 10 to 15 minutes ahead of time. So kind of we can give 10 to 15 minutes of lead time to people, at least intimating them ahead 10 to 15 minutes to 30 minutes that there will be a movement at this location. So watch out or run away. Next slide. Okay, so one other thing I wanted to quickly cover is perceptions of slides and simulation work. So we have not only done the technology, but we have been also looking at the social science, what people think about the risk, because we drive on the road which is prone to slides. Next slide. So here we have actually done two things. One is a survey of the area, understanding what's the mindset of the people living in this area, knowledge, awareness, and perception. And the second is more educational. If we can use simulation tools in educating people that landslide, of course, is a problem, but it may be solvable or solved by their own contribution. So these are two things I'm going to quickly cover. Next slide. Yeah, so here, these are just the objectives I was just mentioning about, so we can skip it. Yeah, so here we've done a survey, and we've gone into the Mandi district, which is where our location is. We have collected data from people living in the area. Next slide. And some of the questions we asked, for example, we gave them this hazard zonation map of the area. Next slide, slide 41. Yeah. So in this, you can see we've given the hazard zonation map. We have circled areas, and the darker the color, it's more susceptible to a slide. However, in their response, people even mark non-landslide or green locations or less landslide prone locations to be, more landslide prone. So people do not understand these maps well. And then when you ask people what are the causal factors in this area, people say it may be an act of God. So this is another view here prevalent in this area. Next slide. So there are misconceptions, and to solve these misconceptions, there are ways out. So one way we have taken is to build a model, and in this model, what we've done, we've taken into account that probability of a slide is a factor which may be determined by the environment, which is rainfall and the geography or the geotechnical aspects of the area, but also by the user or the human living in the area. And human probability is determined by what the human is doing in that area to avert a slide, maybe growing plants, to contributing to building some structures which might prevent landslides. Next slide. So basically, the total probability is kind of a sum of the two probabilities. In this case, the environmental and the user probabilities, human probabilities. Next slide. Yeah. So this is a simulation tool. We call it interactive landslide simulator. So here, basically, the idea is that we give this to a person who lives in the area. The person has to decide how much to invest against the landslide problem in his area. The person earns a daily or monthly income through salary. The person also has property and property wealth. So after people make decisions on their contribution, they receive feedback on different things like probability of the slide, how much money available to them, their property wealth, and they can actually get injured. Somebody in their family can die or due to a slide if a slide occurs, and they could also have property damage. One other aspect is that they could even experience a benign landslide which doesn't cause any damage or any deaths or injury. Next slide. So this is an example where a landslide occurred and nobody died, nobody got injured. However, there was a house destroyed and you lose wealth particularly if that is the case. Now here, if somebody had contributed, the probability due to human factor would have lowered the probability of the slide, and probably the person would have experienced less damages. So we wanted to see how this feedback has an effect on people's perception. Next slide. So next slide. Yes. So we ran an experiment where we had some conditions where people either we had feedback to them. Feedback means they were told about what's happening, whether they are facing a slide, whether they are getting injured, they're facing death, or they're facing injury or property damage. And in another condition, there was no feedback. So they just made decisions and they did not get to know what was the consequence of their decisions. And they made these decisions repeatedly over a period of time, maybe monthly. Next slide. So we had different settings, and I'm going to just skip this. These are instructions basically telling people you live in the area, and this is the mechanics of the game. We have 83 participants collected in this area across different conditions. Next slide, please. Yes. So just wanted to show you the effect. So on the top left, you can actually see y-axis is the investment ratio. Investment ratio is typically a ratio of how much a person could have invested. This is the denominator, and numerator is how much the person actually invested. So in the ILS condition, when they have feedback, they almost are investing half their income because of the feedback they are getting. Whereas if there is no ILS, this ratio drops to almost 37%. So what it tells us that feedback does play a role in making people more, you can say perceptive or more contributing towards the slide. And then the effect is that within the ILS condition, if you give more damaging kind of feedback where people lose more lives, property damage, the contributions are even more. And there's also another interesting interaction effect between damage and ILS. So if you present no ILS, means you just tell them about slides, whether you tell them about more damage or less damage, it doesn't matter. But if you have ILS and you give them more damage, it does cause them to contribute more, almost close to 70% of their income in the game. Next slide. Yeah, so these are some more effects I'm going to skip just to save time. But what it shows is that presenting feedback does have an effect in making people understand the dynamic, and they tend to respond more to landslide problem. Yes, next slide. Yeah, so just to conclude, we're going to talk about, we've talked about landslides causing major damages in the place we live in. We have come up with low-cost technologies that can monitor critical sites. We've also gone regional scale, which Uday was telling through INSAR analyses. We've also been trying to do machine learning in predicting movement. Some of the models are able to accurately do them, prediction of movements, at least in the next 15 to 30 minutes ahead of time. We've also been trying to now look at if we can integrate satellite analyses, which is more infrequent, with a more frequency, with the more IoT-based analysis, which is more frequent, and we get a lot of data pretty quickly. Also, we are trying to educate people through simulation tools like ILS in this area and make people aware about the risks they face due to the problem. So that's kind of, I guess, next slide. Yeah, so these are some of the recognitions and awards we have got. Our Prime Minister visited the place and he reviewed the system. We've also showcased it to the Chief Minister of our state, the Governor of our state. We've also got some awards, and recently we started a company which our students are taking forward to give the systems commercially to the society. Next slide. Yeah, that's about it. So I'll hand back the baton back to Uday. I'm done. Thank you.
Yeah, we're done. Thank you very much. So if you have any questions, we'll be able to take it right away.
Okay, thank you, Uday and Varun. I appreciate that. Very interesting. Okay, so we only have about 5 minutes left in our time, so I will open it up for questions for anybody, any of our speakers today. Please just unmute yourself and feel free to ask your question if you have one. Maybe if the speakers would turn on their cameras, that would be great. Okay, while we wait, I have some questions. Arthur, I have a question about yours. When you're talking about the Kalman filter and it's adding physics, are you actually able to add something like gravity? I would assume that that's what's sort of happening. It's things are moving downhill, and so one of the things would be that you don't expect them to move uphill. Is that the type of physics that you can include with this? Is let's say things have to move in a certain direction?
It's something that we could try to implement, but it's not precisely what we implemented here. I think the main issue with what you are proposing is that sometimes you have also rotation of blocks, and so the tags will actually go backwards. So we cannot really fix this kind of behavior. The kind of physics we use is simply inertial physics, like we just propagate the velocity on the position, and we consider that there is no specific source of acceleration. We propagate velocity on position a long time, and if we don't have correct enough measurement, we consider that the tag will propagate its velocity on the next iteration. Of course, there is there's an aspect of mathematical stability of the filter that has to be taken into account in order to avoid loops, infinity loops. But yeah, that's the kind of physics we use. For now, it's quite simple physics, because at first we tried to implement some kind of model of fluid dynamics in landslides, but there is such a diversity in this domain, and no real consensus, that we tried to implement something quite simple.
Okay, thanks. And maybe Uday and Varun, can you comment on how you're using the gyroscope and the accelerometer data?
Uday, would you like to go ahead?
Go ahead. Go ahead.
Okay. So, good question. Thank you, Dylan. So one question. So the accelerometer data is we actually integrated to get change in velocity, and then further integrated to get displacements. So this is the linear acceleration, and we get linear displacement. Now, on the other hand, what Arthur was also saying, there may be rotational component or rotations. So gyroscope actually allows us to get the rotation or if there is any rolling happening of the accelerometer. And that typically would be in radian per second. So we multiply it with the number of seconds to get the number of radians or degree tilt of the gyroscope from the gyroscope. So basically we get two kinds of data. And as you can see that accelerometer may give three components, Gx, Gy, Gz. So we get three components of displacement, and a gyroscope would also give you omega x, omega y, omega z. So we get three components of rotation. So this is kind of 6 values which we can get from the accelerometer gyroscope.
Okay, thank you. Luca, I see your hand is up.
Yeah, it was a general question. What are the pros and cons of the RFID monitoring approach and the GPS, the GNSS that Tina was showing? If someone can comment on that.
I can give some information about the RFID, maybe not about the GNSS because I'm not using it on a daily basis, but as of now, RFID is rather accurate in comparison with other methods. It's quite simple to implement and quite quick to implement also, and it's very cheap compared. If you want to have I don't know, like 15 points on the surface with displacement monitoring, RFID is quite cheap compared to other methods like GNSS, for example, or wired sensor networks, wireless. Sorry. I would say the disadvantages is, for now, kind of the limiting factor is the range. The tags that we use are not read beyond 50 meters from the antenna. That's why we're trying to develop drone approaches in order to read the tags with a moving antenna. But for a fixed station, yeah, you're basically limited to approximately 50 meters. I could go deeper, but I think one part of the question was asked to Tina. So.
Yes, thank you. So we observed that the main advantages of GNSS was that it's quite accurate, also low cost. It's not so expensive. It's not hard to install. It's quite easy. It provides us with the hourly data, and for us it's very useful because the landslide is remote in the mountain areas, and this is really a good good sensor for us to obtain continuous data on surface displacements. But from the other side, this areas also is very vegetated, and this GNSS antennas needs to the open space, let's say, no vegetation, so we cannot implement it these units, for example, on some part of the landslide that would be really useful to obtain data from that part.
Thank you.
But thank you. I think it was interesting, since these two way of monitoring, they do the same thing basically. Yeah, thanks.
Any other questions from the audience? Otherwise, we'll wrap up. Okay, well, I would just like to thank all four of you again. Those are very interesting presentations. We will post the video online and you will see an email with the link to YouTube for that. Good morning or good night, wherever you are. Sorry for keeping you up late, folks in India, but we appreciate your contribution today.
Yes. Thank you.
Thank you, Darren. Thank you for hosting.
Yep.
Thank
All
you.
right. See you, everyone.
Thank you.
Bye.
Bye bye. Have
Bye
some good
bye.
time.